All right, folks. So let's go and get started. We spent the last couple days talking about measurements, okay? And we've focused in on the numerical portion of a measurement. But remember, in any measurement, what's required then is you have to have a numerical part, and you also have to have the unit part. One without the other gives us a meaningless description. Okay, so a measurement is a description of a quantity that we can actually assign a magnitude to, a number to. Again, like we talked about earlier, measurement is a description of a physical quantity that we can use some type of tool to gauge how big or how small it is. So, for example, a length. When we talk about length, we can take a ruler and we can use that ruler to determine how big or how small that particular length is. However, if all we do is record down a number, so we take the ruler, we measure out the length of a person, for example, and so we get a length of about two meters. And so if all we record down is the number two, then that number doesn't really give anyone else looking at that number any idea of what is being measured. Is the two referring to mass? Is it referring to a time? But if we want to make sure that everyone understands and that the two that we had just written down refers to the length of a person, we also have to make sure we include a unit. Okay? And so therefore then, if we leave out the unit, the number then is meaningless because it doesn't really tell the reader, the person who sees the number, what physical quantity is being measured. Okay, and so what we're going to do here then is we're going to focus it on the unit portion of a measurement. Okay, and so we'll talk about that. We're going to talk about how we deal with these units and what type of units that we use. Okay, so first of all, then let's go ahead and get started here. So when we talk about units, okay, we're going to be dealing with units that are metric units. Okay, we will not use the imperial system, the system of units that we use here in the United States quite a bit. Okay, so the ones you're familiar with, the inches, the feet, the gallons, and the ounces, and so forth. What you typically see, miles, for example, when you are out and about during your day. Okay, so that's the system of units that is used here in the United States. It's a fairly outdated system, not a very good system of units used because when we get to it, when we start talking about conversions, it's very difficult to convert. It's not difficult, but it's more cumbersome to convert between the units and the imperial system because there's no clear or there's no simple relationship between different units. And so when we talk about conversions, when we get to that, you're going to see then that the metric system allows us to relate different units, okay, different quantities of units to each other in a very simple way. And they're all related to each other by factors of 10. And that's what makes the metric system very simple. Okay. And so what we use in science then is a modified version of this metric system, and it's called the SI system. So the SI units basically is a system of units that is based on the metric system. We take the metric system, we use that to define then certain physical quantities. Okay? Now, this is a system of units that was agreed upon by scientists way back in the day, well before any of us was born, back in the 60s. Okay? That allows us to have a system that is fairly uniform in nature, okay, that everyone can agree to, and it's based upon this metric system here. And the reason why the ease of the reason why they chose to use the metric system because it's very simple. Okay? The metric system then is used almost uniformly around the world, and it's used in all the sciences. Okay? The reason why the metric system is so simple to use is because all of the units are related to each other by multiples of 10. We don't have to worry about, for example, 12 inches in a foot. The number 12 is fairly arbitrary. Where does that come from, right? Now understand, the relationships here in the metric system is also arbitrary. Nature doesn't recognize these units. Nature doesn't recognize the way that we've defined these units. Okay. However, we have chosen to use, if we choose to use a metric system, we're choosing to use an arbitrary system that is much easier to understand, much easier to relate, and much easier to use. Okay? And so that's why in science and in almost every other country in the world, they use the metric system. And it's all about doing these conversions here. So if you take a look at the key here is doing these conversions. And what we're going to do is we'll talk about these conversions more when we get to it, but it's doing these conversions here. That is switching between one unit and another. Switching between one unit and another in the metric system is very, very easy. Okay, all right. So that's why we choose the metric system, and that's why the SI, the System International, is based upon this metric system. Okay, all right. So there are basically 7 units in 7 base units in the SI system. Okay, and of the 7, the ones highlighted in red here are the ones that we will use here in chemistry. Okay? The luminosity, the luminous intensity, and the electric current, you'll use that in physics for when you move on. But these are the base SI units that we'll use. So let's go ahead and take a look at each one of these in turn. Okay? So the unit for length, then, the unit for length there, as you notice, is going to be the meter. That also happens to be the metric unit. That's the metric unit for length as well. Now, do you understand this? When we get to it, okay, the metric system has what are called base units, okay, and then we build upon those base units using these prefixes that we'll talk about. Okay, the SI system here is going to be based upon these units here, and so they may not necessarily represent what we call the base unit in an SI in the metric system. Okay, and so what we're going to do then is we're going to talk about the SI system first, and then I'll talk about the metric system and how we can switch between the different units in the metric system. Okay. All right. So with that said, then the unit for length in the SI system is also the base unit for length in the metric system. Okay. All right. So with that said, then we have mass. So we describe length then using the unit meter. So whenever you see the term meter come up, whenever you see the unit meter come up with this symbol here, that's the symbol for the meter, the little m. That means then whatever number precedes it is describing a length. And that's why the unit is so important when we talk about measurements. Okay. All right. So whenever you see the symbol m, or whenever you see the word meter associated with the number, you know that that number is describing a length. Okay. All right. The SI unit for mass then is the kilogram. Okay. Which has this unit here that's gram. So let me just go ahead right here in the space here. So for the SI system, the base unit of length is meter. For the metric system, the base unit is also meter. So those are the same. Okay, both of these. So in the side here, I'm going to write in the metric unit. Okay. All right. For mass, though, the base unit for mass in the metric system is the gram. Okay. However, in the SI system, we use the unit kilogram. Okay. And so kilogram, if you notice here, the word gram appears in kilogram right there. Okay. And so what we're going to do is we're going to talk about what these prefixes mean here. So what we've done is we've added a prefix to the base unit gram here. So let me go ahead and make sure that you understand that what I have written in blue is the metric system. We're comparing it to the SI system here. So this is SI, this is metric here. Okay. All right, so the gram then is the base unit for mass in the metric system. The SI system then takes that base unit of grams and they add the prefix kilo to it. Now, what that does is it changes the size of the unit. Okay, it changes the size of the unit. How it changes, we'll talk about this in just a moment. Okay, we'll talk about what that kilo does. Okay, but the reason why the SI system does this is because typically outside of, typically when we deal with on the macroscopic level, I mentioned this in the very first day of class, and you'd be able to make the connection between macroscopic and microscopic. On the macroscopic level, the gram is a very small quantity. Okay, on a very, very small quantity. You take a gram of something, it is a very small amount of that particular something. Okay? So what we do then with the SI system, we want to scale it up a little bit, and so the unit kilogram refers to a mass that is bigger, that is 1,000 times bigger than the gram. The reason for that then is that on the macroscopic level, it is easier to refer to the mass of an object in terms of kilograms than in terms of grams. And that's why the SI system chose to adopt the kilogram as its base unit as opposed to the gram for the metric system. Okay? And so that's going to be a key difference there. And that's the only difference between the metric base unit and the SI base unit here. Okay? All right, so remember, the SI system is a system that is based upon the metric units. that was adopted by a convention of scientists around the world back in the 60s that makes describing measurements a little bit easier. Okay? And so they chose to adopt the kilogram versus, as opposed to the gram when we do measurements. Okay? All right. So that's the base unit. So whenever you see the symbol kg or the symbol g, we'll talk about this. And so the base unit here is also letter m. The base unit here is symbolized by the letter g. So whenever you see the symbol kg following a number, then you know then that that particular number refers to a mass, how much matter a particular substance has. Okay? And so we'll talk about that a little bit more when we get to chapter 2. Hopefully we'll get to chapter 2 on Monday. But we'll refer to that, okay? And you'll talk about we'll talk about what matter is and how we can measure matter. Here, this is a reference to a measurement of how much matter, how much stuff a particular object has. Okay. All right, so that's the base unit for mass. Okay. If you take a look at temperature, then the base unit for temperature in the SI scale is the Kelvin. In the metric system, it is degrees Celsius. Okay. Now here in the U.S., we use Fahrenheit quite a bit. Fahrenheit, again, the reason why we don't like to use Fahrenheit in the metric system in science is because it's a very difficult unit to work with, especially when it comes to conversions. The conversion between Celsius and Kelvin, very straightforward. It's 273. We add or subtract 273. That's going to be the magic number that we work with. We'll talk about that a little bit towards the end of the discussion here. Okay. All right. So that's those are the two units for temperature. Degrees Celsius is the metric unit for temperature, and Kelvin is the metric unit for. Is the unit temperature unit for SI. And so therefore, if you see the letter K, the symbol K, or the symbol not C, you know then that whatever number precedes it is referring to a temperature. We'll talk about what temperature is. Temperature is a measure of relative heat. So we'll talk about that as well a little bit later in this course. Okay? All right, and so with time, then time's pretty much the same. Both of them have the unit seconds. Okay, and so therefore, if you seconds. Okay, so the metric unit for time is seconds. The SI unit for time is also seconds. So those are the same there, in the same way that there's length. Okay, the symbol for time is S. Okay, now, so we use the unit. We use seconds, not hours, not minutes, to refer to time intervals. Okay? And so therefore, whenever you see the letter S following a number, you know then that particular number is referring to a particular time interval. Okay? All right. And so with that said, then I think meters, kilograms, Kelvin, seconds. I think most of you probably are familiar with meters, kilograms, seconds, Kelvin. You may not, but you are familiar with degrees Celsius. The one new one here, and this is something we'll learn much more about later on in this course here in chapter 10, I introduced this unit mole. Okay? The unit mole here, and it's symbolized by the symbol, it's symbolized by the letters MOL. The mole then is a measure of the amount of substances, okay? The amount of a particular substance that we have. We use the unit mole, and there's a relationship between moles and the number of objects that the amount of the substance we'll talk about in chapter 10. That allows us then to describe the amount of substance that tend to be very small. We typically don't use the unit mole to describe the objects around us because it ends up being a very, very big number. And so what we'll do then is we'll hold off on talking about the mole. Okay? And so this mole then is a new unit that we'll learn about, but I'm going to hold off on talking about that until we get to chapter 10. Okay? All right. So let's talk about how we can deal, what we do then as we deal with the relationships here. So we talked about the kilo and how it's related to the unit, what happens when we add it to the base unit of grams. And so the kilo represents then a prefix. Okay? Let's talk about what these prefixes are. Now, some of you are familiar with these prefixes already. You learned about these probably in your first algebra class. Okay? And so these prefixes here, what they do then is they are related. What they do is we assign each one of these prefixes to a certain factor, a certain multiple. They serve then to remind us that there is a multiplier that is related to them. Okay, so for example, we talked about the unit kilo. Okay, and the unit kilo then is related to this multiplier here, okay? So it's 1,000. So 10 to the third is 1,000. So let's make sure you keep that in mind. 10 to the third represents 1,000. So what happens then is if you add the prefix kilo, okay? So we saw the base unit gram. We saw then that the SI unit per gram, metric unit for mass is grams, okay? And so the gram then is the base unit, okay? And so if we add the prefix kilo to the gram, what we're saying then is this new unit here is 1,000 times larger than the base unit grams. Okay, so if you take a look at this, then 1 kilogram, if we take a look at this, if we understand what the prefix kilo means, it means then that it will take 1,000 of these grams here. So whatever unit that it precedes, that it comes before, that we add it to, it's going to make that particular unit 1,000. It refers to a unit that is 1,000 times larger. Okay? All right, so that's what happens when we add the prefix kilo in front of the base unit grams. So make sure you understand that. What we did is we took the kilo, we add the base unit here is grams. Okay? So 1 kilogram is 1,000 grams. That means then the prefix kilo is 1,000 times larger than the gram. Okay? All right, so with that said, then let's you'll need to know that. Okay, so we talked about that. Let's go ahead then. Let's refer to a few of these other ones. Okay, so the ones that I've given you here, the commonly used prefixes. Okay, there are many others. Okay, the ones highlighted in red are the ones that we'll use quite a bit in chemistry here. So what I would suggest you do then, and this is something that you should probably do, memorize the kilo, memorize what the centi is, and memorize what the milli is. Okay, micro, nano, and pico. If you choose to memorize them, that's fine. Okay, but that's because we use them quite a bit, especially when we get to chapter 4, when we start talking on the atomic scale. The unit milli, the unit micro, nano, and pico will come up quite a bit because we're dealing with a very small object. Okay? And so let's go ahead and let's continue to look at these prefixes here. So with that said, then if the kilo represents a unit, if you add the prefix kilo to the base unit, and if that new unit then represents a unit that is 1,000 times larger, what happens then with centi? Okay, well, let's continue, and we'll continue working with unit gram here, but obviously you can add these prefixes to any of the metric units. Okay, well, let's take a look at the what happens with centi. Okay? So with the centi, then this represents a unit, if you add it, that is 100 times smaller. So the multiplier here is 10 to the minus 2, which means then this is going to be, remember with expanded notation, multiplying by 0.01, which means that we're going to make the unit smaller. So that means that if we add the prefix centi, so let's go ahead and take a look at the gram. If we add the prefix centi in front of the gram, okay, if we add the prefix centi in front of the gram, that means then that whenever we do that, that represents then a unit that is 100 times smaller. So it's going to be 0.01 grams. Okay, so the centigram is a smaller unit than the gram, and how much smaller? It is. It's only about a hundredth of a gram. Okay, so therefore we have this relationship here. So whenever you have the prefix centi, what we've done then is we've made a unit that is smaller than the base unit. Okay, so how much smaller? 100 times smaller. So you take 100th of a gram, and that will be equal to 1 centigram. Okay, all right. So let's continue on with this real quick then, and then we'll finish up with this. Okay, so with the milli, so whenever you put the prefix milli in front of the gram, in front of the base unit, you're making a new unit that is 1,000 times smaller. So if we expand this one, then you'll notice then that it's going to be 0.001. Okay, so therefore then, if you take the unit milli, the prefix milli, and you add it in front of the base unit grams, that 1 milligram then is going to be equivalent to 0.001 grams. You've made then a unit that is smaller. Okay, why would we do this? Why would we do this? Well, let's understand this here. Okay, in the same way that when I talked about the SI unit of kilo, okay, I said then that the kilogram is there. We use the kilogram in the SI because we're referring to in the macroscopic world, most objects are fairly large, and so the unit gram is an impractical unit. And in a moment, I'll give you a sense of how big and how small these units are. Okay, but it's impractical to use the gram to describe objects. Say, for example, your book or how your mass or the mass of your laptop or whatnot. Okay, and so we use the prefix kilo. We add that to the gram, which makes then the gram unit 1,000 times larger. Okay, and that now becomes a simpler unit to describe. So instead of describing your mass as being, let's say, 7,000 grams, okay, we say then it's just going to be 70,000 grams. We say that it's just 70 kilograms. Okay, so it's easier to use. It's a smaller number. It's more efficient. Now, same thing holds true then for the prefix centi and milli. So if we're talking about very small objects, okay, the unit gram then becomes a very big unit. And so if we're going to go ahead and describe then, let's say the mass of 3 grains of salt, table salt, for example, okay, using the prefix gram then makes then for a number that is very, very small. And so the idea here then is that by adding the prefix milli or adding the prefix centi to it, we can then convert that particular unit and that measurement into a number that is a little bigger than 1 and a little bit easier to use. Okay? So the whole idea behind changing and adding these prefixes is to use now to obtain a unit now that is more usable for a particular situation. And so again, in a moment, I'm going to point these things out to you really quickly, and then you'll see how this works. Okay? All right. So with that said, then let's go ahead and I'm going to finish up here. Micro. Let's continue on. It's 1,000,000 times smaller. Okay. So if you add the prefix micro, so the prefix micro in front of the gram, for example, so 1 microgram. Okay. Let's go ahead and let's take a look at what we have here. 10 to the 6th then it's going to be 0.0000, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Yeah, so 10 to the 6th, it's 1,000,000 times smaller. So therefore then, if you have a microgram, it's going to be 0.0001, 2, 3, 4, 5, 6 grams. And that's how it works. And so you can imagine what nano and pico is going to be. Okay, and so you have 10 to the 9th, which is a billion, 10 to the 12th, which is going to be a trillion. Okay, and so with that said, then what we're doing is we're making a very small unit. Okay, so when would we use the microgram? We would use it to describe, let's say, one particular grain or one particular molecule of sucrose, for example, or sugar, or nano. We would use that to describe the particular atom, the mass of a particular atom. Okay. All right, so that's what we would do there. Okay, so make sure you're familiar with these units here. Make sure you're familiar with these prefixes. Know what the kilo unit stands for. Know what the centi unit does. Know what the milli unit does. Okay, so we'll be dealing with those, especially when we start talking about conversion. Okay. All right, let's continue on here, folks, and and let's take a look. So what I'd like to do now is give you a basic comparison, give you an idea of how these units work and how they relate to one another. Okay, so we just talked about the prefixes. Okay, and so I want to give you an idea of scale. Okay, when we would choose to use a base unit, and when would we add in a prefix in order to change the scale, the size of that particular unit. Okay, so I'm going to focus in on the length, volume, mass, and then we'll talk about temperature and energy towards the end. Okay, all right. So the SI base unit for length is going to be the meter. Okay, so let's think about the scalar. I mean, I think if we just give you the word meter, it's very difficult for you to think about it in terms of just that word. It's fairly abstract. What is the meter? Okay. And I already said then that these units here, all these units, whether we're talking about metric units or imperial units, these are all arbitrary. Nature does not recognize the meter and how we define the meter. Okay? All right, so the meter is roughly the distance, if you take a look at it, the unit, 1 meter. 1 meter is roughly the distance between the doorknob in a typical door and the floor. Okay, so 1 meter, a 1 meter length is typically the length from the doorknob down to the floor. That's typically about a meter worth of length. Now, how did we come about at this particular definition? How did we decide then that 1 meter represents this particular length? Again, it's arbitrary. Okay? However, it allows us then to have a standard that we can all agree to. So if you wanted to go out and you wanted to buy a meter's worth of cloth, for example, if we didn't have a standard that everyone agreed to, you can go out to one shop and they can give you a certain length and they say, hey, there's your meter. And you go to another shop and they give you that length and they say, well, that's your meter. And that's what I define as a meter. So there's no agreement. There wouldn't be any standard. And so you end up getting ripped off because you were paying more money or an equal amount of money for a smaller length of cloth. So therefore, what we have done in science and what we've done is that we've all agreed, we've said then that there's a certain length that we will call a meter and we will all agree to that meter. Again, nature does not agree to that meter. Okay? Nature doesn't recognize these lengths. We as humans in society have said then that we're going to accept that this length here that is roughly from the doorknob down to the floor is our unit of meter. Okay, that is our 1 meter. Now, in the past, what they did is they actually, in the past, they actually had a piece of metal, fairly inert piece of metal. We don't want the metal to expand or contract, and so they measured it out. Okay, and everyone agreed to this particular metal. It's fairly inert. We'll talk about it later. Okay, inert metal. Okay, and they said, okay, this piece of metal and this length piece of metal represents 1 meter. And so what they did was they took that piece of metal, they took it to a Navy base somewhere on the East Coast. They stuck it into a vault. They sealed it up, and they kept it at fairly constant ambient temperatures, and that was the standard for the meter. Okay, that's what everyone agreed to. Now the problem with that is that and we talk about this later. All objects change with temperature and they change with time. They undergo reactions. They change. Okay? And so the reason why they chose a fairly inert metal, meaning that it doesn't change so much, but understand everything does change with time, but it doesn't change as fast. And so what the problem with choosing a piece of metal, even if you put it in a very stable environment with temperatures being constant, it still changes. And so you can imagine if a little piece of it starts to get worn away and you lose that, or it starts to expand a little bit because the temperature goes up, okay, then our base unit of meter, that 1 meter, changes its length. And so we lose a standard, we lose the opportunity to say, okay, well, this particular unit represents the meter. Now, what we've done now in science, we switched to a standard that is a little bit more stable, and that is we use light, the distance that light travels in a particular amount of time, and that's the standard we use for the length of meter, okay, which is much more consistent. The light doesn't change. The light doesn't change as much in a vacuum and in an inert environment, okay? All right. So with that said, you may think to yourself, well, why do we use the unit meter if it changes, if the standard changes? Okay? Well, because it's much more consistent than, let's say, the unit foot. I mean, the unit foot has a really interesting history, and I'm going to leave it up to you to find that out. But the reason why we stuck with the meter and why we use the meter in the SI in our SI system is because it's easy to use. It's easy. The conversions is what's easy. And so therefore then, like I pointed out to you then, if we take the unit meter here, in each one of these cases, if you look at it, we have the prefix, a different prefix highlighted in red attached to the base unit meter. By adding that prefix to the base unit, we've changed the length. Okay? We've changed the length that we're referring to. And so we talked about the meter then as being the distance, roughly 1 meter being the distance from the doorknob down to the floor. If we add the prefix kilo, and that's what we have here in front of it, the distance now that we're talking about, that we're referring to, is a distance 1 kilometer. And so make sure you understand that what we're referring to is 1 kilometer. Okay, a 1 kilometer distance, and I'm sorry, that's kind of messy there, but a 1 kilometer distance refers to a length now that is not the length between the doorknob and the floor, but the length of 5 city blocks, roughly 5 city blocks. That's a lot bigger length. And so you can imagine that if we wanted to measure the distance between here and San Diego, for example, we don't want to measure that in units of meters. That'll give us a really big number, a really, really big number. Okay? Instead, then we can use kilometer then, and it gives us a number then that's a little bit more reasonable. Okay. All right, so that's why we have the kilo, and that's why we choose to use the prefix kilo. Okay, we add the kilo to the meter, and we already talked about this. And so if we add that, that is roughly equal to 1,000 meters. Okay, all right, so that's what we have right there. All right, so let's go ahead and let's continue on then. If we add deci, I didn't really ask you to memorize, but deci then, if you take a look at this, the prefix decimeter then, deci, and you add it to the prefix meter, represents a length that is roughly now the length of an orange, which is 10 times smaller than the meter. Okay, so if we take a look at this 1 decimeter, then is going to be equivalent to 0.1 meters. Okay, so that's what we have there. Okay, so what we've done is we've taken a unit then. So we've gone then from the length from the doorknob down to the floor to the length that represents the diameter of an orange, which is a much smaller length. Okay, so that's what we have. So the prefix deci allows us to do that. There is the prefix milli. Okay, the 1 millimeter, we add that to the base unit of meters, and we said then that that is a unit that is 1,000 times smaller than the meter, and that's roughly the thickness of a dime, and you were able to measure that. Hopefully, quite a few of you got close to that, not quite too close, but you got close to that. And so measuring not the diameter here of the dime, but the thickness of the dime. Okay? All right, and so with the micrometer then, micrometer, we add the prefix micro, and I'm running a little low on timer, folks. The prefix micro here, you add the micrometer, you add 1 in front, then you have then a unit that is approximately equal to 0.000001 meter, 1,000,000 times smaller than the meter. Okay, all right. So that's why we use the prefixes. Okay, and so what I'd like to do now is let's just quickly run through and let's talk about the rest. Okay, so for volume, then we typically use the unit liter. Okay, for the SI unit for volume. I didn't include that in the previous slide. I don't think I did. So yeah, so we didn't have that on the table there. Okay, so make sure you have then the volume as well. Okay, volume we use in SI unit of liters. Okay, I'm sorry, cubic meters. Okay, what we typically use then in chemistry is the unit liter. Cubic meters then is is the volume. If you notice here, this is basically we take the unit of length and we raise to the third power. We multiply it by 3 dimensions. Okay, so therefore the SI unit for volume is going to be the cubic meter. We tend to use the unit liter here more often. Okay, we tend to use the unit liter in science, and so in chemistry, then we use the unit liter. Okay, all right. And so with that said, then a liter's worth of volume is roughly about a quart of milk. Okay, so if you take the quart of milk, that's going to be the liter. So that's going to be our base unit. Okay, for volume, for a base unit for volume. Okay, and so with that said, then you can imagine if we take the prefix micro and we add it to the base unit of liters, we have then a unit then that is 1,000,000 times smaller. So let's go ahead and write that in. It's going to be a 0.000012345 liter. Okay, so we have a unit that is 1,000,000 times smaller than the liter, base unit of liters here, and that's roughly the volume of a single crystal of table salt. Okay, all right. Just kind of give you an idea of another unit that we use then is the cubic centimeter. You'll see that quite a bit. That's going to be the volume of a single cube of sugar, if you've ever seen it. Okay, that's a little bit bigger than this microliter here. Okay, but then this is a unit that is based upon the SI unit. So we saw then that the SI unit is the cubic meter. Okay, so let me go back here and point out to you. Okay, so this cubic meter, that's the SI unit. You can see then that here, we're still dealing with the length unit here. That's the cubic centimeter, okay? And that's the volume here. There is a relationship that we're going to take advantage of, and so keep this in mind. So make sure then that when you do this, make sure you write this down somewhere, okay? That this is a relationship that we're going to make use of, okay? And here you notice then that the liter, here's your milliliter here. That's a symbol for milliliters. And so what I've done here is I've given you then 1,000 times bigger than the liter, okay? Or you could say that the milliliter is 1,000 times smaller. So this would be 0.001 liters here. But this is a standard conversion here, a standard relationship that we can take advantage of when we refer to the volume. Okay, so keep that in mind, and when we get to conversions, we'll talk about that. Okay, so let me go ahead and finish up really quickly here, and let's talk about mass. Okay, unit of mass, remember, is kilogram. SI unit for mass is kilogram. Okay, and with the kilogram, then what we have then is the mass of a kilogram is roughly that of your book, your chemistry book. If you put it in your hand, and if you hold it, that you're holding then a kilogram's worth of mass. Okay? Now, when I talk about this here, do keep in mind then that mass and weight, I told you to hold your book, mass and weight are not quite the same concept. We tend to think of them the same, but they're not. So make sure you keep, and we'll get back to this and we'll discuss this much more in the next chapter when we start talking about chapter 2. But mass is basically the measure of the amount of matter. Okay, so mass is the amount of matter that that a particular substance has. Okay, weight though is a measure of gravity, the gravitational pull. Okay, on a particular object when it's on Earth here. Okay, so weight and mass are not the same quantities. They're not the same description. Okay. All right. So with that said, then the gram, which is the base unit for mass in the metric system, the mass of that is roughly about the mass of a dollar bill. So if you want to hold a dollar bill in one hand, hold a chemistry book in the other hand, you can tell the difference between their masses. Okay? And so the mass of the kilogram is 1,000 times larger than the mass of the gram. Okay, so you can feel that difference by holding the book in your hand and holding the dollar bill in your hand. Okay, so with that said, then adding the prefix micro in front of the gram, then we have a mass of an object that is 1,000,000 times smaller than the mass of the dollar bill here. That's roughly one single particle of baking soda. That baking soda, if you can isolate a single particle, its mass, that if you hold that in your hand versus the mass of a dollar bill, you should be able to tell the difference there, just like you are able to tell the difference between the weight of a book and the weight of the dollar bill. So right now I'm kind of using the term mass and weights interchangeably, but again, like I pointed out in the previous slide, they are not the same. Yeah. All right, so milligram then is equivalent to about 10 grains of sodium chloride. You take 10 grains out, that's the mass of equivalent to 1 milligram. Okay. All right. Let me quickly finish up here. Let's talk about temperature really quickly. Okay, and then we'll finish up here. Obviously, with this particular discussion here, you don't have to. There's nothing you have to write down. I just want to talk about units with you to preview this for you. Okay, and so temperature then is measured in degrees Celsius or in Kelvin. So temperature then is a measure of how hot or how cold an object is. Okay, so make sure you keep this in mind, that the temperature itself is not a measure. I'm sorry, let me backtrack here. Heat is an energy. Heat is energy. Okay, and so what temperature does is temperature is a measure of the relative amount of heat that one object has or one area has relative to another. So temperature is a measure of the heat content of a particular substance. Okay? And so basically, heat then the temperature measures the heat. Now, heat does flow, and we'll talk about this when we get to the second semester when we talk about thermal chemistry. But heat does flow. It flows from areas of hot down to cold. Okay. And so with that said, then a few other things that I want to point out to you. Heat then causes objects to expand. You heat an object, it's going to expand. You take the heat out, and it's going to contract. Okay, and so there are two units for to measure temperature. The Celsius unit is what we use quite a bit. That's named after the Swedish astronomer way back in the day. And the Celsius unit is fairly easy to use because it has two temperatures that are the relative that are the marking points for the Celsius scale, and that is 0 degrees Celsius and 100 degrees Celsius. And what's important of those two temperatures? Freezing point of water, 0 degrees Celsius. Boiling point of water, 100 degrees Celsius. And so if you have 100 equal marks between 0 and 100, each mark then represents 1 degree Celsius. Okay? Now the Kelvin scale is even easier to use because the Kelvin scale represents there's a single temperature that is the starting point there, and that's absolute zero Kelvin. 0 Kelvin then, and we'll talk about this much more when we get to thermal chemistry. Okay, 0 Kelvin then represents the absolute coldest that we can get. Okay, and so this 0 Kelvin scale represents the temperature at which there is no more heat whatsoever. Okay, and so with that said, then what does it allow us to do? If that's the bottom, if that's the lowest temperature we get, we will never get negative temperatures on the Kelvin scale. It is possible to get negative temperatures on the Celsius scale because we can get colder. We can get colder than the freezing point of water. And so with the Kelvin scale then, it makes it easy because you can't get any lower than 0. And so therefore all of our temperatures then will be positive. Okay. All right. So with that said then, the boiling point of water is at 373 Kelvin and the freezing point of water is 273, which will allow us then to do very simple conversions, which I'll talk about with you in class. Okay, and that's the relationship between Kelvin and the Celsius scale. Okay. And so I'm going to use this here to begin our discussion of conversions a little bit later, but at this point then I'm going to stop. I've gone a little bit over time, And so hopefully this gives you a chance to understand what the units of the units are and how we use them. Okay. All right, very good, folks. And so now the next step then is we're going to put it together. We're going to take the measurements, and then we're going to talk about how we can change measurements and the sizes of measurements. Okay? That'll be in the next discussion. Okay. All right, folks. Have a good day, and I'll see you a little bit later.